With that little notification. Let me turn off where I got sounds coming from. So, good evening and happy Tuesday. I promise I'm gonna get it together, y'all. It is Tuesday, and I think there's one more date I had to change. We'll see it when we see it. So, good evening and happy Tuesday, as well as happy GHOE, everybody. Before we begin, last session we finished looking over the material for the second exam on differentiation, and that would be chapters 5.1 to 6.3. We had the intro and limit definitions of the derivative. We had basic differentiation rules, which are the constant, power, constant multiple, and linear combination rules. We had the advanced differentiation rules, which break down into the power and quotient rules, which chapter 5.3, and the chain rule, which is chapter 6.1, which prepped us for implicit differentiation, and 6.2, which prepped us for related rates in 6.3. All right, so since this little chunk of calculus is over, we're going to just take today to review the topics before diving into new material. So I'm just going to be going back over everything that I had for you before, and also because it's GHO, and I want y'all to get out of here and have some fun. With that being said, just a couple disclaimers. It's going to be a lot of info and a little bit of time because if you think about it, it is all the sessions that we've ever had kind of just wrapped into one. So that means that questions are encouraged extra today. If there's something that you wanted to see, or something that you wanted to see or go back over, I can do that. Especially instead of going over the material that we've already seen. Um, Additionally, I usually like to go pretty in depth with topics and go over them from the ground up. Today, instead, I'm going to be sacrificing that usual depth in favor of, just casting a wider net, covering more things instead of one thing really deeply. And we got to beat the Broncos.
Yeah, F them. They beat the Eagles. I don't like them. We off.
We got to beat the Broncos. We can't let Bo Nix lead a game winning drive. As a Super Bowl favorite, that's just, I wouldn't do that personally. Thank you guys for the Kava recommendation. Yes, Thursday we're not going to be here.
No Bills.
We don't celebrate the Bills here either. I would kick you, but I'm not allowed to. I've lost my train of thought. Yeah. No session Thursday. I would say Wednesday, but you guys don't meet Wednesday. Today is just the only day of the week. So yeah, without further ado, let's go ahead and dive into the things that we've taken a look at. So starting off with 5.1, we were introduced to the limit definitions of the derivative. I have definitions here. Technically, there's only one definition of the derivative using the limit, but we were given two formulas, which essentially mean the same thing, but I digress. So first, we were given this formula, which says that the slope of a tangent line is equal to the limit as our x value that we're looking at approaches some number that we're given, a, and we said that this is equal, I'm sorry, yeah, the slope of the tangent is equal to that limit as x approaches our given number of the function value of x minus the function value of a over x minus a. Right? We broke that formula down. We looked at what it really meant. And we said that using limits, we can essentially split the 1 point into two by setting the distance to be an infinitely small value, right? So we know we can't take the slope of, or I'm sorry, yeah, we can't take the slope of 1 point on a line. We always need 2 points to take the slope. So we said we're going to imagine 2 points and then just move them as close together as we possibly can, and then they would essentially function as one. Right, so a more robust definition is the one that is the actual limit definition of a derivative. And this one just says that, hey, we could have any point on the graph. We don't need to be given a point A. So this one is broken down as the derivative of our function f of x, also can be written as dy dx, y prime, or d dx of the function f of x is equal to the limit as h goes to 0 of the function value of x plus h minus the function value of x over h. Right? And we're saying that this is really identical to the one we've seen above where we were given a point, but instead in this case, we don't know a point on the graph, and we're just taking any point x and any point x plus h that is infinitely close to x, right? So the process for solving derivatives using the limit definition is as follows. We know one, we're going to find the function value of f of x plus h, and we do that by plugging x plus h in for every x. After that, we're going to find f of x plus h minus f of x, and then simplify that. We're going to put that over h and simplify that, and then we're going to apply the limit as h approaches 0 once we're in our simplest form. So a quick example I have here, we've seen this one before, but we're going to find the derivative of f of x, f prime of x, if f of x is equal to 4x squared plus 3x. I know using the power rule that this 2 is going to come down, multiply in front to this 4, give us an 8x. 2 minus 1 is 1. So I'm not going to write the 1 exponent. We know that x is raised to the first power here. And then we can drop off our variable whenever it's raised to the first power. And we take the derivative of it. So I know that the answer to this problem, using the power rule, is going to be 8x plus 3. Now I'm going to find the derivative using the limit definition. So first, we are to find f of x plus h, and we're plugging in x plus h for every x. So I'm going to say f of x plus h is equal to 4 times x plus h squared plus 3 times x plus h. My 4 is going to come down. And using the definition of what a binomial squared is, I know that I'm going to have x squared plus 2xh plus h squared. And then I can just distribute this 3 to get 3x plus 3h. If I then distribute my 4, I'm going to get 4x squared plus 8xh plus 4h squared, excuse me, plus 3x plus 3h, right? And from here, I've found my f of x plus h in its simplest form. Now I want to add my f of x to this, or not. I said add it because we're appending it, but I meant subtract my f of x. Excuse my language there. So f of x is just 4x squared minus 4x squared plus 3x.
Wouldn't that be minus 3x?
In parentheses. Yes, you're correct. So we're going to distribute this negative since we're subtracting all of f of x off. And this is all going to come down to be f of x plus h minus f of x equals 4x squared plus 8xh plus 4h squared plus 3x plus 3h. Then we distribute this negative to get minus 4x squared minus 3x. From here, I want to simplify so I can put this all over h. So I'm going to look for like terms. I have an x squared term. I'm going to do this in pencil. I have an x squared here, and I have an x squared here. I have a 4x minus 4x, or, I'm sorry, 4x squared minus 4x squared. So those are going to cancel. Next, I have an xh term here. I do not see another xh, so this is going to come down. Next, I have an h squared term, and that's also going to come down. Just underline as I go. I have an x here, and I have an x here. That's 3x minus 3x, which is 0. And then I'm left with this 3h on the end here. From here, I'm going to put this over h. And immediately I see that I can get rid of this h in the denominator by dividing an h off all the terms up top. I can either factor or just do it term by term. I'm just going to factor to make it easier to see where I'm taking my h's from. I didn't mean to do that. So if I pull out an h from each of these terms, 8xh divided by h is 8x. 4h squared divided by h is going to be 4h. And 3h divided by h is going to be 3. This is over h. And now these two are going to cancel. So I'm left with 8x plus 4h plus 3. I'm now applying the limit as h goes to 0 of this. And this is just going to drop my 4h term off. So I'm left with 8x plus 3. And we said this is f prime of x. If we go up to our power rule work above, we can see that our answers match. So that's how you find the limit definition, or I'm sorry, that's how you find a derivative using the limit definition of the derivative. Moving on with our derivatives, we then learned our basic differentiation rules, which allow us to take derivatives a little bit easier than that. We know that the derivative of any constant is 0, as long as that constant's a real number. I can't speak for the imaginary numbers because I don't know. We then learn the power rule, which states that when we take the derivative with respect to a variable, and that variable is within the derivative, and when we take the derivative with respect to a variable, essentially, we can take the exponent of that variable, multiply it into its coefficient, and then subtract 1 off the exponent. We know because we use that rule the most frequently. The constant multiple rule states that if we have a constant being multiplied into a polynomial and we're trying to take the derivative of that polynomial, we can pull the constant out and then multiply it into the derivative later if we find that that makes it easier to take the derivative. Many cases, you'll just apply the power rule to each of the terms and you won't really need to do this, but you can if you'd like. The constant multiple rule basically just sets up the linear combination rule, which says that we can apply this across terms whenever we're adding and subtracting polynomials. Right? So if I have a number that I'm multiplying into a polynomial, I can pull it out and I can apply the derivative to each of the terms in that polynomial. So using the basic differentiation rules, we're just going to walk through and find each of these derivatives. So we said that using the constant rule, the derivative of any constant is 0. So A, derivative of 9 is 0. And for B, the derivative of pi is 0 because those are both constants. We're going to assume that we're taking the derivative with respect to x. So using the power rule for C, we're going to multiply this 3 in front to our coefficient of 4 to get 12, bring our variable down, and then subtract 1 off the exponent to get 12x squared. Doing a bit of algebra for D, we know that root t is just t to the 1/2 from the definition that if we have x raised to the a power, and we're taking the bth root of that, that's going to equal x to the a over b. Bth root is kind of funny to say. Bth root. This is t to the first power, and we're taking the square root of it, so it's t to the 1/2. Then we can use the power rule. We're going to multiply this 1/2 down in front to the coefficient of t, which is 1. Bring our variable down and subtract 1 off the exponent. We have a negative power, so we can simplify this if we really wanted to by moving t to the denominator and flipping the sign on the power. So we have t to the 1/2 in the denominator. And we know that t to the 1/2 is equal to root t. So we get a final simplified answer of 1 over 2 root t. Similarly for e, we can rewrite our 1 over x to the third to be x to the negative third power if we bring it to the numerator and flip the sign on the exponent. From here, I can apply the power rule by multiplying this negative 3 in front to the coefficient of 1 to get negative 3. I bring my x down and I subtract 1 off the exponent to get negative 4. So I get negative 3x to the negative fourth. But if I really wanted to, I can bring my x to the denominator and flip the sign to get negative 3 over x to the fourth power. Next for f, I have pi x to the 10th. I'm going to multiply this 10 down in front. Pi is just a constant, so we can treat it like the coefficient of x to get 10 times pi. Bring my variable down and subtract 1 off the exponent. E to the x is a special case. where its derivative is itself. If we have e raised to the power of something times x, we're just going to bring that coefficient of x in front and then keep everything else the same. If we wanted to derive this again, then this is going to be a squared e to the ax, so on and so forth. Next, we have a linear combination rule. Essentially, we're just going to be applying our derivative to each of the terms. The derivative of x to the fourth is 4x cubed plus 4, and 2 is a constant. Same thing for I. We multiply this 4 in front to the 2 to get 8x to the third plus 9x squared minus 5, and 7 is a constant. For j here, I'm going to zoom in and get a smaller brush because there's some rewriting to do. This first term, we're just going to take it normally using the power rule. 1/3 t cubed. I'm going to multiply this 3 in front to the 1/3 to get 1 for my coefficient and subtract 1 off the exponent minus 2. This is going to be t to the negative second power. Negative 2 times negative 2 is negative 4. I'm sorry, positive 4. It's going to be plus 4t. And we have a negative third power since we have t to the negative second minus 1. I can now move this t to the negative third to my denominator and make it positive to get 4 over t cubed. This minus root t, we already said, is going to be minus t to the 1/2. This 1/2 is going to get multiplied in front. I'm just going to rearrange these. This will be 1/2 t to the negative 1/2 power. Then I'm just going to rewrite this as 1 over 2 root t. And pi is a constant, as we know by now. So those are the basic differentiation rules in action. I trust that you know those because you've been using them forever at this point. So moving on to the advanced differentiation rules. And for these, I don't have examples because they're kind of more lengthy and I kind of want to get y'all out of here. So we're just going to walk through these and just talk about them, look at them, because I trust that, again, we've been using them. So the product rule states that when we're taking the derivative of a product of two polynomials, we can apply the following formula because we cannot just distribute the derivative to both and say that this is equal to f prime of x times g prime of x. This doesn't hold up. So we say that if we're trying to take the derivative of two polynomials being multiplied by each other, that is the original first polynomial times the derivative of the second one, plus the derivative of the first times the derivative of the second. Or if you prefer it in u's and v's, it's u times v prime plus u prime times v, where u is your first polynomial and v is your second one. For the product rule, it really doesn't matter which order you do the operations in or which polynomial is which because it's commutative, right? You could do it in any order, but as we'll see in a second, not all rules are commutative, some are associative, and the order in which you do things and pick things does matter. So we have the quotient rule, which is also a part of chapter 5.3. And it states that when we're trying to take the derivative of two polynomials which are being, divided against each other, we can't just apply the derivative to each, distribute it to each term and then take the derivative and say it's f prime of x over g prime of x. That doesn't hold up. So whenever we have two polynomials being divided and we're trying to take the derivative of that, it's represented in the following function, which is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, and the order for those does matter, and that is over the denominator squared. Or if you prefer it, like me, in u's and v's, where u is your numerator and v is your denominator, we're going to have u prime times v minus u times v prime over v squared. Right? And the steps are identical to the product rule steps. Essentially, we're just evaluating the equation. And finally, our chain rule states that whenever we're trying to take the derivative of a composite function, in which we have a function inside of another function, we can, again, not just distribute the derivative to each function and say that it's f prime of g prime of x. Instead, we have to apply the following formula when we're trying to take the derivative of f of g of x, which is f prime of g of x times g prime of x. Right? And that chain rule set us up for further differentiation when we can't just take the derivative of the function itself directly. Right? So we know that an explicit function expresses one variable in terms of another, right? If you were to plug in a number for one variable, you would be able to solve for what the other one would be. Then an implicit function expresses a relationship between two variables without being able to solve for one. So two examples I have are x squared plus y squared equals 25 and sine xy equals 0.356. For this one, if you try to solve for one variable, say let's try to solve for x here, we get x squared equals 25 minus y squared. Then we take the square root of both sides to get x is equal to plus or minus 25 minus y squared. Obviously, this isn't a direct answer. We don't know which version of x we're going to get. So this is an implicit function because of branching, right? We have two separate branches which the function can take. This one, I have two variables wrapped inside of a transitive function, and I can't do anything to separate x and y, right? We're taking the sine of x and y, and those have to be inside. So this is another version of an implicit function that you may see, right? So some of which are difficult or impossible to isolate for y, which we see in our transitive function version, like, right, it's literally impossible to isolate y or x, and others have multiple branches, right? So with the techniques above that we went through, the product rule, chain rule, quotient rule, as well as the basic differentiation rules, we're unable to apply the derivative to these functions because we can only take the derivative with respect to one variable at a time. Implicit differentiation is a technique to work around this, in which we employ the chain rule to variables that we're not taking the derivative with respect to. Right? So when an expression is implicit and unsolvable for both variables, we can still find the derivative by employing implicit differentiation. The steps are here. They're available to you. I can send this out as well. This is the video being uploaded later. So I'm not going to read through these. We've been over them. You know them. So I'm just going to move on to our example, in which we're using implicit differentiation to find the derivative of the following function. So here, our first step is to take the derivative of both sides or apply the derivative operator on both sides. It's asking me to find the derivative of y with respect to x. So I know I'm going to have to take the derivative with respect to x. So I'm just going to write it over here. And I know technically it's illegal, but I don't feel like writing ddx twice. So I'm just going to write it like this. Don't do that. Going through and differentiating each term using implicit differentiation, I'm going to take the derivative of every term with respect to x. This first term I have to employ it on. So the derivative of y to the fourth is 4y cubed. And then I have to take the derivative of my inside term, which is just y, and that's dy dx. This comes from our chain rule, where we have the derivative of the outside function, where we keep the original the same. That's our 4y cubed. And then we multiply it times the derivative of the inside. Our inside is y. The derivative of y with respect to x is dy dx. The next term is ugly, so I'm just going to differentiate the one after it. The derivative of 4x, or x to the fourth, with respect to x is 4x cubed. I'm going to leave some space and differentiate my right side now. It's going to be equal to 3 The derivative of 3y is just 3 times the derivative of y, which is dy dx. And the derivative of any constant is 0. I don't need to write minus 0. For this term here, I see we have one polynomial being multiplied into another, so I have to apply the product rule. I almost said the chain rule. We will have to apply the chain rule, but not yet. I'm just going to start setting up my product rule here. And it's defined as u prime v plus v prime u. My u is 2x, my v is y squared. The derivative of 2x with respect to x is just 2. And the derivative of y squared with respect to x is 2y. And from our chain rule, we get a dy dx. Plugging into our product rule formula over here, we have a 2 times v, which is y squared, plus v prime, which is 2y dy dx, times u, which is 2x. I'm just going to multiply these directly to get 4xy dy dx. So I can plug that in up here. We have a 2y squared plus a 4xy. Give me a little bit of space, please. Dy dx. Great. I'm just going to erase the product rule work because we're done with it. Now that we've gone through and differentiated all of our terms, I want to group what I'm solving for on one side. I'm trying to find dy dx, which is what the problem is asking for up here. That's an ugly circle. Let's get a prettier one. One more time. There we go. We're solving for dy dx. So I'm going to group all my dy dx terms on one side. This term can stay. This one has to move. This one has to move. This term can stay, and this one has to move. I'm going to write my terms that are staying first. I have a 4y cubed dy dx, and I have a 4xy dy dx. I'm moving over this 3 dy dx, so I'm going to flip its sign. And then I'm moving my other terms, so those signs are going to flip as well. From here, I'm going to factor out my dy dx's since that's what I'm solving for. I want to be able to divide things off easily. So 4y cubed dy dx divided by dy dx is 4y cubed. 4xy dy dx divided by dy dx is 4xy. And taking off the last one, I just get 3. It's going to be equal to the same thing over here because I haven't done anything on this side. And now to get dy dx by itself, I can just divide these terms off. To get dy dx is equal to negative 4x cubed minus 2y squared over, I said that like it was final, 4y cubed plus 4xy minus 3 as our final answer. From here, we moved into related rates, which states that, well, just a little bit of background. It doesn't state anything yet. We know that if two quantities are related, one changes over time, so too does the other. Otherwise, the relationship wouldn't hold, right? The circumference and radius of a circle are related with the formula C equals 2 pi r. And as one grows, so too does the other. Same thing if it shrinks, right? As we increase the circumference of the circle, its radius is going to increase at the same rate relative to the circumference. Go figure. So we can use implicit differentiation on this equation to find the rates at which both of our variables are changing. Once we do that, we get the rate at which the circumference is changing is equal to 2 pi times the rate at which the radius is changing. Here are the steps to solve related rates problems. I'll pause here for your sake, and then we can move into our example. This example is the ugly one that I didn't show you before when we were initially doing related rates because we ran out of time. So I'm going to get to it now, and I think this is the last example we have for the day. Yep. So this problem states that sand is falling off a conveyor belt onto a conical pile at 50 cubic feet per minute. The diameter of the base of the cone is always 5 times greater than the height. How fast is the height of the pile increasing when the pile is 12 feet high? Our first step for these related rates problems is to always organize our variables because that's the easiest part to mess up. So let's get our variable bank. I'm going to get my thicker brush back so it stops exposing my handwriting. So we were given that sand is falling onto a conveyor or off of a conveyor belt onto a pile that is in the shape of a cone at 50 cubic feet per minute. So that's a rate at which a volume is changing. So we were given dV/dt. And if you look off to the side, you'll notice I cheated and I wrote the volume of a cone formula there for myself because I don't know it off the top of my head. Um, you know, it's okay. It's okay to not know things. We said dV/dt is equal to 50. We will save that for a second. We were given a moment of time where the height is equal to 12 feet. We have a relational formula over there. And that's really all we were given. So now we can look at the ratio that we were given, because if we look at the volume of our cone formula, oh, and we're solving for dH/dt, I should write that. If we look at the volume of a cone formula, you'll notice that it uses 3 variables. So if I were to differentiate that implicitly, I would be given 3 rates of change. And in this problem, I was only given one. If I only have one rate of change, or I'm sorry, if I was only given one rate of change and I have to solve for two, it's not going to be possible because I don't know how the other rates are affecting each other. Luckily, this problem gave me that the diameter of the base of the cone is always 5 times greater than the height. And with this ratio, I can establish a rate between, or I'm sorry, I can establish a replacement for one of the variables in my volume formula. So that way I don't have to solve for 2 rates, right? If I know what one thing is in relation to another thing, then if I know one of those things, I know what the other is at all times. So if I know that the diameter of the base is always 5 times greater than the height, so the diameter is going to equal 5 times the height. The diameter doesn't really do anything for me though, because it's not in my volume formula. But knowing from geometry, the diameter is always 2 times greater than the radius. If we look at our example here, the diameter is labeled, and half of this diameter is going to be the radius that we actually care about in our formula. So that relational formula is given as d is equal to 2r. So that means that 2r is equal to 5h. And since I'm solving, or I'm sorry, since I'm trying to solve for dH/dt, I'm going to replace my r in the formula. Yes. Since I'm solving for dH/dt, when I implicitly differentiate, I want to be able to pull that out so that I can solve for it. So I want to replace the r in the volume formula with h. So I need r to be something in terms of h. So I'm going to isolate my r. to get r is equal to 5 halves of h. And that way I can replace r in my volume formula. So now that I have everything that I need in my variable bank, I'm going to solve this problem using implicit differentiation. So know that the volume is equal to 1/3 of pi times r squared h. But we know that we're replacing r with 5 halves of h. So that 1/3 pi is going to come down. We said we're replacing r with 5 halves of h. We're going to be squaring r still. We have an h on the outside. If I simplify this just a little bit before I want to differentiate here, 5 halves squared is 25 over 4. H squared is h squared times h. That's going to be h cubed. So now I can go ahead and apply my differential. Again, this is illegal. Please don't do it. And I'm taking the derivative with respect to time here since I care how the cone is changing over time. So here I'm going to get dv dt is equal. And I'm going to simplify this just a little bit more. I'm going to multiply this 1/3 into this fraction to get 25 over 12. Or actually, no. It's going to be easier if the 1/3 stays since I have h to the third power. That was right. So if I differentiate this ugly term here, this 3, this whole thing right here is the coefficient of h because it's going to be a constant if I pull it off, right? I can multiply 1/3 times pi times 25 over 4 to get a number. So I can treat that as my coefficient. I'm going to multiply this 3 in front, and that gets rid of my 1/3. Subtract 1 off the exponent, and since I'm taking the derivative with respect to t, I need a dh dt over here. So we said we're getting rid of the 1/3. We keep everything else the same. We're subtracting 1 off the exponent, and we're multiplying 1 dh dt. Mm, not quite. Not quite. Let's multiply this 1/3 in to get this over 12. Yeah, because that's going to make breaking it down easier. So this is going to be 3 pi instead, times 25 over 12. H squared dh dt still. And from here, we've differentiated, and let's see if we can plug things in. So I was given an h, I was given a dv dt. I have an r, but I already replaced it. And let's look at our variables. I need to solve for dh dt. So I have a dv dt, which is 50. This 3 pi can come down. This 25 over 12. I have an h, which is 12. And you'll see why I simplified the fraction now. And then dh dt is what we're solving for. From here, I can see that I can cancel this 12 and this exponent here and rewrite to get 50 equals 3 pi times 25 times 12 times dh dt. 25 times 12 is what? 300? 300 times 3 is 900, and I don't want to scroll up. And then we can divide off our 900 pi to get a final answer of 50 over 900 pi. That's what our DHDT is. And it was on the right. I'm just going to move it over and then put units on this thing. The HDT is height. Height is one dimensional, so this is going to be feet per minute. And I'm not going to bother simplifying that fraction. It's good enough, even though I could divide by 50. So, with that, that covers the bulk of the material for the second exam, whether it is in the past, in the present, or upcoming. Best of luck to you whenever you take it or have taken it. If you have any further questions, feel free to reach out to me by email. It's there for you. Also, the session is going to be uploaded on YouTube if you want to watch back over it. So I have notes. I'm free to meet via email if you want to, or I'm free to meet via Teams or Zoom or whatever you want to do. Just reach out to me via email, whatever you want to set up. Also willing to send out notes for any chapter you'd like. I was able to find some optimization notes, so I can go over those when we next see each other. I think that'll be next Tuesday. Uh, but I will be probably out next Tuesday because I'm traveling from Wednesday to Wednesday, and I won't be checking my email often if you reach out to me. But besides that, that's all I have for you. I appreciate you all for coming out. I will put the attendance up.